Hello, my name is Andrés Domínguez, and I will present our paper titled Addressing Contingency in Algorithmic Misinformation Classification Toward a Responsible Machine Learning Agenda. This paper is the result of an interdisciplinary collaboration between science and technology studies scholars and data scientists. In this study, we look at machine learning classification models, which have been increasingly used by social media companies to assist in the moderation of misinformation, and similarly any other content that might be deemed undesirable and subject to moderation. These models became more prevalent in the context of the COVID-19 pandemic, where major social media platforms admitted relying more on automation and less on human decision-making for content moderation. And this led to more posts being taken down, but also to a surge in accepted appeals, which in other words means false positives. So how do these models work? They rely on so-called ground truth datasets, which contain examples of truthful and false information, and this could be drawn from large corpora of knowledge such as Wikipedia, or as in the case that we're focusing here, the verdicts of fact-checker organizations around the world on claims that circulate online at a given time. Fact-checkers are particularly valuable during newsworthy events such as elections, pandemics, wars, etc. So to develop these models, data scientists take the sources of truth at face value, that means as objective and reliable. And given the scale at which these models operate, sometimes affecting billions of users, decisions as to how they are built and deployed can have significant ethical, political, and epistemic implications, which are rarely addressed in technical papers, and hence we wish to address here. So to critically assess these techniques, we go back to discussions within philosophy of science and social studies of science about what constitutes a fact. This scholarship reminds us that there's a social dimension to facticity and truth. In other words, facts are socially constructed, situated, and contingent. Scientific facts, for instance, need to be observed, communicated, and circulated in society, and for that reason, who we consider to be sources of truth is based on legitimacy, which is gained through credential expertise, trust in scientific institutions, or credibility. Feminist scholars in particular have challenged the loose language of objectivity and neutrality in knowledge production, as it hides the forces that shape knowledge production, such as research priorities, special interest groups, sources of funding, etc. And this is true also of fact-checkers, who perform an important epistemic role in society, but can not only be fallible in their assessments, but also they can be biased in different ways, for example, in the topics and claims that they select to fact-check. So why is this important for machine learning moderation? As these models seek to automate the practice of fact-checking, the inherently social nature of truth becomes black-boxed and intractable, meaning that any biases or errors can be blindly reproduced by algorithms as these practices are scaled up, but also any accountability for errors is ultimately replaced by a logic of model performance and accuracy, and I will return to this in a minute. These observations are not intended to be a relativist attack on science and journalism and institutions, but more as a caution that is key when we examine the assumptions that underpin machine learning classification models. In our study, we explore the construction of these algorithms empirically through an interactive method that we call coethnography, involving the co-authors of this paper, 2 social scientists and 2 data scientists, in the construction of the machine learning classification model, and we also looked at comparable efforts in the technical literature. We expand on this methodology in a forthcoming publication, and you can also read more about our methodology in our paper. In terms of findings, we advance what we call algorithmic contingencies. We define these as key moments during machine learning model development, which could lead to different future outcomes, uncertainty, and harmful effects. We identify algorithmic contingencies in each of the steps in the construction of a machine learning misinformation detection model, throughout problem definition, through training and testing, and finally in model deployment. As a caveat, the contingencies that we identify here are not intended as a comprehensive list, but to signal researchers that certain decisions can have significant downstream impacts. In the next few slides, I will highlight some of the contingencies we identified in each of the steps, as well as their implications and why they are significant. I won't go through all of them, but you can find them in our paper, and also if you can pause this video, you can read through them. So starting with problem definition, we found that researchers use different theories and definitions and strategies to detect misinformation. For instance, some models might use the definition of fake news, while others might use definitions of disinformation, and they might differ. And similarly, different strategies might use different empirical studies to come up with a technique of detection. So as researchers abstract their problem definition and translate them into an algorithmic model, these differences become intractable and flatten under a framework of misinformation classification. The second step is the choice of inputs and outputs. And for instance, decisions as to what kind of variables are used are often guided by technical and cost feasibility factors about, for example, what kind of data are available or are more easily accessible. And one of the implications of this is that sometimes proxy variables may be used in lieu of causal relationships due to their reduced cost. And this could lead to spurious correlations between inputs and outputs. One example of this is the use of signifiers of humor to signal the presence of misinformation. The third step involves the use of ground truth data for model training, or what we call ground truthing. There are many conditionalities in here in terms of the validity of the training data and the legitimacy of the sources to predict misinformation. One of them, for instance, is that fact checkers do not always agree on their verdicts over the same claim. And this could be because of biases or mistakes, but also because not all information can be categorized as simply true or false. There might be more nuance involved. As a consequence, models using discrete outputs, such as for instance true or false, might lead to a loss of nuance or amplify errors and biases. The next step is model validation. Here we want to highlight that metrics of performance are normally the prime indicator of the utility of a model. And these metrics in turn influence the extent to which a model can be trusted to inform moderation decisions such as censoring or downranking pieces of content. And since models are expected to perform at scale, performance metrics are not always a good indicator of how they will perform in topics or cultural contexts that are different from those used as benchmark for evaluation. Not only that, but performance metrics make it difficult to account for all the contingencies that we surface here. Finally, we highlight some wider issues with model deployment. Perhaps the most important one to highlight here is that these models are often positioned as solutions to a complex problem, following a utilitarian approach where some error or harm is acceptable. This framing shifts the responsibility to the producers and consumers of misinformation, thereby underplaying the responsibilities of social media platforms in enabling the circulation of undesirable content. That also means the onus of algorithmic failures and harms falls on users. So what's next? What do we do about the contingencies that we highlight here? We note first of all that algorithmic contingency is not something that can be solved, but that needs to be addressed by machine learning researchers. We propose 3 tentative paths toward responsible practices in algorithmic moderation detection, which we argue are also relevant for algorithmic content moderation at large. The first one is about extending the practice of reflexivity beyond datasets. That means not only reporting on the quality and limitations of datasets, but on the potential limitations, cautions, biases, and even conflicts of interest as they pertain to the whole process of model construction. The second recommendation is about conducting more situated and timely evaluations. In practice, this would entail updating datasets in real time, even if that means reducing their size to reflect the availability of new information, and also using benchmarks of evaluation that are sensitive to context, events, topics, and languages. Finally, we advocate for better accounting and reporting of uncertainty. This is not only about quantitative assessments of uncertainty, but also qualitative assessments. And this should accompany metrics of performance and be used to provide a better understanding of a model's potential limitations and failures. Thanks very much for listening.